Hello and welcome back. In this video, we are going to talk about the design of simply supported concrete beams. A beam which is supported by a roller at one end and a pin at another end is called a simply supported beam. In our case, the beam is 22 feet long. The amount of dead load it's going to support is 1 kilopound per foot. In addition to that, it's going to support a 2 kilopound per foot of live load as well. In the dead load, the self-weight of the beam is not included. For the specific example, the compressive strength of concrete is 4,000 psi and the yield strength of steel is assumed to be 60,000 psi. The height of the beam is assumed to be 10% of the span and the weight of the beam is assumed to be half of its height. In the ACI code itself, there is a specific table given out of which you can take the initial dimensions for different types of structures. But for this example, we will go with these assumptions. So the first step in here is to calculate the dimensions and the weight of the beam. For the dimensions, the height of the beam will be 10% of its span, which is 0.1 times 22, which equals to 2.2 feet. If we convert this into inches, we'll multiply it by 12, it will be 26.4 inches, and here we will assume it as 27 inches. This is because the labor at the site cannot work that accurate amounts like 26.4 or 26.2. That's why we assume the height of the beam to be 27 inches. For the weight of the beam, it was assumed to be half of the height of the beam, which will be 0.5 times 27, it is 13.5 inches. And we will assume this one and increase this to 14 inches as well. In the ACI code, the height is somewhere between 2 times to 1.5 times its weight. And the unit weight of the reinforced concrete is 150 pounds per cubic foot. Since we are going to multiply the height and the weight into the unit weight of the concrete, we have to convert the inch square to foot square. From here, we know that 1 foot is 12 inches and 1 foot square will be 144 inches. Now we will multiply the weight by height and we will multiply that by the unit weight of concrete. This will result in 394 pounds per foot, which means that the beam itself will weigh 394 pounds per each foot. In the next step, we are going to calculate the ultimate weight and the ultimate moment, which are exerted on the beam. For the ultimate weight, we have 1.2 dead load plus 1.6 live load. In the dead load, we have the dead load exerted on the column and the self-weight of the column. While in the live load, we only have the 2 kilopound per foot weight, which was exerted on the column. The summation of these forces will be 4.783 kilopounds per foot. In order to calculate the ultimate moment for a simply supported beam, we have the formula to be WU, or ultimate weight, times L squared, the span squared, divided by 8. From here, we know the ultimate weight and we know the span of the beam. Once we multiply and divide these, the result will be 294.8 kilopound times foot. Once these are calculated, we are going to calculate the steel area required to support this moment. And for that, the general formula for the steel area is rho times B times D. Rho is the amount of steel required in the cross-section. B is the weight of the concrete beam that we had previously calculated as 14 inches. D is the effective depth. We had the height to be 27 inches. We have to deduct a specific amount in order for the steel bars to be protected from any type of external damages like fire and etc. So in order to calculate the amount of D, we have to deduct a specific cover for the steel bars, which is also known as clear cover. That clear cover as per ACI code is 3 inches in places where they were exposed to soil, for example, footings. But in beams and columns, it could be around 2 inches. In this specific example, we will assume that to be 2.5 inches. So the effective depth of the concrete beam will be 27 inches minus 2.5 inches, which will be 24.5 inches. We have the values for both B and D in here. We have to calculate the value for rho. For this, we have a formula which is given as below. We also can use the tables given in ACI code. From this formula, we have the compressive strength of the concrete and the yield strength of the steel. But the only value that we do not know until now is the nominal resistance of the section. For that one, we have the formula to be ultimate moment divided by phi times b times d square. This value will be 467.7 pound per square inch. From here, we can calculate the value for rho, which is 0.00842. And from here, we can obtain the value for the steel area required, which is 2.89 inch square. Now we have to provide exact steel bars to the section of the beam. We will take 3 number 9 bars, which will be around 3 inches square. In the US customary system, the diameter of the number 9 bar will be calculated as dividing the number by 8, which will be 1.125 inches. If you calculate the sectional area of this bar, it will be around 1 inch square, which is pi times d squared divided by 4. Now, if you provide 3 of this, the total amount of steel area will be 3 inch square. The next thing is to check the results that we have obtained. Number 1, we are going to check the rho that we have obtained. The maximum rho in here as per ACI code is 0.0181 and the minimum is 0.0033. This is for flexural structural elements such as beams and slabs. For columns, this value is different. So the value should not exceed this and should not be lower than this value. From here, we can obtain the value for rho to be 0.00875, which is lower than the maximum value and higher than the minimum value. So this is okay. For the ultimate moment should be lower than the nominal moment or the moment that the section can resist. In order to calculate the nominal moment, we use this formula. In here, everything else is clear. For example, we have the area of steel, the yield strength of the steel, and the effective depth of the beam. And the only thing that we don't know in here is the height of the compressive block and the beam. In order to calculate that, we have this formula, and the height of the compressive block will be 3.78 inches. If you replace the values in here, the amount of nominal moment will be 3,662 kilopounds times inch, or 305.2 kilopounds times foot. This is bigger than our ultimate moment that we calculated in the previous steps, which means that the amount of moment that the section can support is way bigger and way higher than the moment that's actually exerted on the section. So this check is okay as well. Finally, we have to illustrate our design section. We have a beam section for which the effective depth and the clear cover sounds to be 27 inches and the weight of the beam is 14 inches. We have provided 3 number 9 bars to the beam to support the loads which were exerted on the beam. I hope you have found the content of the video helpful. If you did so, consider subscribing to the YouTube channel and following us on Instagram or LinkedIn. Thank you very much for watching.